Okay, so it's a real pleasure to introduce Marten Lohstroh. He's been working as a graduate student in my group for 6 years now, which is, I think, a pretty respectable time for completing a PhD thesis. And I'll tell you a little story, but basically, I don't know, 3 or 4 months ago, I started to really arm twist him because I told him that he really had enough results to write up his PhD thesis and that he needed to get it done and get it filed so that he could then start earning a more reasonable income. I basically told him that I was going to sign it in December, whether it was written or not. And that kind of built a little fire under him. And so he's producing a really very nice piece of work. It's not quite finished yet, but it's looking really good to me. And so it's a real pleasure to see it all coming together. So with that, I'll let Marten take the floor and tell you all about it.
Okay, thank you for the nice introduction, Edward. And thank you all for taking the time to attend my dissertation talk on reactors, a deterministic model of concurrent computation for reactive systems. So let me start with the most important part of this presentation. Some might say that pursuing a PhD is all about personal achievement, but going through this process has taught me that there's actually very little that one can truly do without the support of others. And that is not to mention the metaphorical shoulders that we stand on as researchers, but I'm truly grateful to the people that helped me throughout this journey that started when I came to Berkeley quite a few years ago. And I'm very excited to see that many of you are here. I'd like to start with thanking my advisor, Edward Lee, who has been a tremendous source of inspiration and has given me freedom, opportunity, and invaluable mentorship. Edward wrote in his thesis that his advisor, Dave Messerschmidt, treated him like a colleague well before he deserved it. And I'm very lucky to say that I feel the same way about my advisor. So thank you for paying it forward, Edward. I would also like to thank the other members of my committee, Gul Aga, Sanjit Sesha, and Alberto Sangiovanni Vincentelli. I'm very honored to have them on my committee. My dissertation work is based to a significant degree on Gul Aga's work on actors originated by Carl Hewitt, who has also joined us here today. Sanjit and Alberto have influenced me profoundly with their ideas, and I've always felt encouraged by them throughout my years at Berkeley. I would also like to thank Sarush Bateni, Xiaokao Lin, Edward Lee, Christian Menard, Alexander Schulz-Rosengarten, and Matthew Weber for their hard work on the language, the runtime, and the compiler toolchain that we've built together. And I think Jeronimo Castellón, Kong Liu, and Reinhard von Hangsleden for allowing and encouraging their students to sink their time into this project. I'm also thankful to my co-authors, and I would like to give credit to Andres Huns for his very early involvement in the conception of reactors, and Inigo Inser for his substantial role that he played in the formalization of reactors. I also thank Ivan Vivid, formerly known as Chris Shaver, for the many insightful discussions that I've had with him about models of computation while he was a student here at Berkeley. I would also like to thank my colleagues in the DUP Center, my former office mates, and the many wonderful people in the department and on campus that I had the pleasure of interacting with during my time as a graduate student. I've learned a lot from you, and I'm grateful for the great friendships that I owe to Berkeley. Lastly, I would like to express my gratitude to my family, my parents, my wife, Rusi, and my son, Luca. I know it hasn't been easy on you, and I couldn't have done it without your love, your patience, and your unwavering support. So thank you. So before I came to Berkeley, I got interested in concurrency in computing. Back at the University of Amsterdam, I had familiarized myself with some formal tools for reasoning about concurrency, such as process calculi and process algebra. And I had learned about classical problems like deadlock, life lock, and starvation. These are problems that do not appear in ordinary sequential programs, but they loom large in systems that are comprised of multiple concurrent processes. At the time, I liked the problems, but I didn't like many of the solutions that I was seeing, particularly from an engineering perspective. I agreed with Edward, with what Edward famously called the problem with threads, and I thought it made more sense from a design practice to eliminate problematic system behaviors in concurrent systems from the scope of possible behaviors, rather than to allow them and then spend precious resources on trying to verify that no problematic behaviors exist. A set of constraints that intentionally reduces the space of program behaviors such that a desired property is satisfied by construction is called a model of computation. This approach, based on what Alberto famously calls freedom of choice, has been wildly successful in areas like digital signal processing and hardware design. The work that I present here today should be viewed through that lens. In my dissertation work, I focused on achieving one very specific property, and that is determinism. So it's hard to overstate the success of deterministic models. Examples are synchronous digital logic, instruction set architectures, and sequential software, just to name a few. The reason for the success of these deterministic models is that they're easier to test. Their correctness and safety is easier to verify, and simulation of these kinds of systems is more practical. But what do we mean exactly by a deterministic model? It simply means that given the initial state and inputs, the model defines exactly one behavior. I just wanted to quickly show this definition so we're all on the same page about this. We'll get back to the definition a couple times throughout this talk. Before we continue, I would also like to clarify the notion of reactive systems, which is prominently featured in the title of my thesis, of course. Interestingly, one could say that many of the computers that we surround ourselves today with are not actually computing in the classical church Turing sense of the word. Computational behavior is transformational. It's about taking input and hopefully producing some desired result. The purpose of reactive systems, on the other hand, is to maintain an interaction with their environment for a prolonged period, possibly ad infinitum, without ever terminating. Not everything is computable, of course, and not every computation terminates, but the goal of computation is to terminate and produce a result. For reactive systems, termination is typically a fault condition. Think of a computer operating system, or worse, an aircraft flight control system. When we evaluate the correctness of computation, it usually suffices to consider inputs and outputs and not the particular steps taken to achieve the result. But in reactive systems, correct behavior is expressed in terms of traces of ongoing interactions with the environment. And if we want to compose two computations, we can do so sequentially, or we can interleave them. But in reactive systems, we speak of true concurrency because processes may not be interruptible. We may not be able to pause them, and their actions are not necessarily atomic. Lastly, time is not a semantic property in computation. It's not part of the model. We usually say that a computer performs better when it computes faster, but a slower computer is not incorrect. In reactive systems, we usually care about when reactions occur, meaning we have to treat time as a semantic property. For instance, a pedestrian detection system in an autonomous car that detects a pedestrian too late isn't just slow, it's wrong. And the consequences could be grave. As it turns out, making time a semantic property in our programming model can actually help us achieve determinism. There's actually a long tradition of so-called synchronous languages that leverage the semantic notion of time to achieve determinism. Mostly targeted at real-time control software, they're known for allowing programmers to write modular and mathematically precise system specifications, to simulate, test, and verify them, and to automatically translate them into embedded code. Very well known are Signal, Estrel, and Lohstroh. A notable success is SCADE, with this application to safety-critical software in nuclear power plants, aeronautics, and railway systems. And what all these languages have in common is that they are actually full-blown programming languages in their own right. As I will explain, our approach is slightly different in that regard. Very much related also to the work of my thesis are SC charts, from which we leverage the idea of sequential constructiveness. And the model that I propose in my thesis borrows from the synchronous reactive principles that underpin these languages. And it could be characterized as what Stephen Edward would call a sparse synchronous model. One challenge that we're facing is that we increasingly need parallelism in our computing platforms to achieve performance goals, scale with big problem sizes, accommodate highly variant workloads, and deal with the inherent complexity of the system that we build. In cyber physical systems or embedded systems, an interesting tension is rising. Where we used to think of them as highly specialized, embedded, and resource constrained, we now see them become integrated with resource-hungry AI systems. Think of, again, autonomous driving that require very powerful hardware and sometimes even access to the cloud. Yet the parallel and distributed computing community has, in a sense, turned its back on determinism a long time ago. Its prevailing paradigms include actors, but also publish, subscribe, and server-oriented architectures where everything is asynchronous. And of course, asynchrony is also good for latency hiding and useful for avoiding deadlocks, for instance. But the loss of determinism is troubling, especially when these technologies make their appearance in safety-critical systems. These days, people are building systems in ROS or AutoSAR, and they're caught by surprise when they encounter non-determinism. Last year, I co-authored a paper specifically on this topic with my colleague Christian Menard at TU Dresden. And there we took a demonstrator application of the newly proposed AutoSAR AP framework, which stands for Adaptive Platform. This concerned an automatic braking system, and we were able to show, even in this demonstrator application, just how badly non-deterministic it was. So the focus of this work is to reclaim determinism in these sorts of systems. And as is the case for synchronous languages, our solution involves leveraging a semantic notion of time. Reactors are based on an interesting mix of ingredients from synchronous languages, actors, object-oriented models, discrete event systems, distributed systems, and even hardware description languages. In a way, some of this work can be seen as an attempt to follow Tony Hoare's advice and prioritize consolidation of good ideas over the proliferation of new ones. Of course, there are also novelties in reactors, but we'll get to those later. It's not easy to create a successful new programming language from scratch. Depending on who you ask, there are hundreds of them, or even thousands, and yet the popularity contest plays out among just a handful of them. The problem is that it's extremely difficult to convince individuals, companies, and communities to abandon languages that they've invested in. The costs are simply too high. We saw an opportunity to bring deterministic concurrency and a time-aware programming paradigm to a larger community, not by creating our own language, but to compete with these giants, but by creating a deterministic coordination layer that can exist symbiotically with these existing languages. We implemented this coordination layer in the form of a language we call Lingua Franca, or LF for short. Programs written in LF compile down to several different target languages, including C, C++, TypeScript, and recently also Python. And data dependencies are explicit in our model. And the execution of an LF program follows a discrete event semantics. Reactions to events are logically instantaneous, and the logic inside of reactions is given in verbatim target code. So here's an overview of the compilation process of a Lingua Franca program. At the top left corner, there's a program that gets parsed and validated. If there are any syntax problems, we report them directly. One very nice feature that we have in our IDE is also the synthesis of diagrams of our code that can be very insightful, seeing what the, understanding what the code does. What we then have to do is, after parsing, generate target code that gets combined with a runtime system, and that then has to go through a target compiler. Or if it's an interpreted language, it will be interpreted directly. And this is the second validation step that has to happen, because the compiler of the target language might also find problems, and those also have to then send back to the Lingua Franca programmer for fixing. And what rolls out at the other end is an executable or an interpretable program. So there's one key aspect of Lingua Franca or reactors that is novel. It is the capability of relating events across different timelines. And among those timelines, we distinguish two different kinds of timelines: logical ones and physical ones. Okay, so what do I mean by that? As in synchronous languages, logical time progresses in discrete ticks, and no sooner than the work for that time step has completed. Physical time, on the other hand, increments continuously, and two subsequent measurements of physical time, given enough resolution, of course, will always differ from one another. It keeps moving forward. But the picture is more complicated in the physical case, because simultaneity is a relativistic notion in physics, meaning that it depends on the frame of reference of the observer. And that makes it not very practical as an abstraction for engineering systems. In logical time, on the other hand, simultaneity is an absolute predicate, making it very easy to reason about. But we can't just stick with logical time. If we care about interactions with our software with the physical world, we may want to react to stimuli from the environment. What time should we associate with those? We may want to impose deadlines to ensure that our computational system can keep up with its physical counterpart. Or we may want to define system behavior that spans locations that are physically distributed. We might also want to respond when assumptions about the timing of events in the physical world are broken. And all of these things require us to relate events across timelines. And in Lingua Franca, we provide abstractions for that. As I already mentioned, Lingua Franca is based on reactors. To understand LF, we first need to understand reactors. So let me briefly walk you through some of the key aspects of reactors and their execution semantics. Okay, so reactors have ports. Values written to ports constitute events that can trigger reactions. Reactions are totally ordered within the reactor that contains them. And if two reactions within the same reactor are triggered simultaneously, the order of declaration determines which one executes first. Reactions also need to explicitly declare the ports that they access, and if they don't, then a compilation error will result. They will not be in scope. Reactors can also be triggered by a special trigger called startup. It's represented by a bullet here, which is only present at the very first instant of a reactor's lifecycle. Similarly, we have a shutdown trigger, the lattice shape over there, that is only present at the last instant of a reactor's lifecycle. An event at one port can trigger more than one reaction. Not all reactions are triggered at every time step. And following the sequential constructiveness principle known from SC charts, when two reactions, I should say, set the value of the same port, only the last written value survives, and no downstream reactions are triggered or executed before that value has settled. Reactions can also be contained in one another, and the container can have its own reactions. Within the scope of a containing reactor, ports can be connected, and cycles in the connection topology are permitted as long as they don't introduce any cyclic dependencies between reactions. So this connection here is totally fine. Now let's go through a simple execution run. The startup action triggers the first reactions of A and B. Let's assume a value is produced in the first reaction of A, which then triggers the second and third reaction in A. These reactions execute in their prescribed order. So 3 comes after 2. If either or both produce a value, this triggers a second reaction in B, and the second reaction in B and the first reaction in C. Note that these two reactions have no ordering relationship or data dependency between them, so they can execute in parallel. After all this, we're still at the very first logical time instant, and there are no more reactions to be triggered. So we're stuck. How do we advance time, and where to? For this, we need a logical action represented here. Let's assume that the third reaction of A schedules a logical action with an offset of 20 milliseconds every time that it is triggered. The first time that the action triggers reaction 3 of A, the other two reactions are actually not triggered because the startup action is absent. And then the second reaction of B and the first reaction of C might be triggered again. And now we've reached the end of a tick. The program will just continue and react like this every 20 milliseconds. Finally, if a timeout was specified or shutdown was requested, then the last reaction of B is triggered. Now let's look at some Lingua Franca code. This code specifies a main reactor with 3 contained reactors and connections between them. Timeout of 1 second has been specified, so this program only runs for 1 second. We also have a shorthand notation for the periodically scheduled logical action that we saw in the previous example, and we call them timers, right here. This timer has no offset, the first argument, and it has a period of 100 milliseconds. Logical actions can also be used to specify logical delays between reactions of different reactors, and that can be done with something like this delay reactor over here that uses a logical action again, and now with a 50 millisecond delay. So here's the output of our simple program. We first compile it with LFC, which generates C code that includes our runtime, and then it compiles with GCC. It then executes the binary. And as expected, the printed time values start with an offset of 50 milliseconds due to the delay and continue with a period of 100 milliseconds due to the timer. Notice that the elapsed logical times are exact, and the physical times approximate the specified timing. And this is because Lingua Franca events are not released into the system until the physical time has surpassed the tag of the event. And of course, if so desired, the physical times can match the logical times much closer when this code is executed on hardware that admits better control over timing, such as FlexBread or Patmos. This particular one was just done on my laptop. Because logical delays are of common use, we also provide a shorthand syntax for those. The LF compiler carries out an AST transformation that wires each connection with an after through a kind of delay reactor that we saw in the previous example. Now let's discuss physical actions. Consider the following simple cyber-physical system. It has a sensor, a controller, and it performs some analysis, and an actuator. When the sensor starts up, it creates a thread that monitors the keyboard. It also passes along a reference to its physical action called response, so that read input here can schedule a response whenever a new keystroke event is detected. And since this happens asynchronously in a separate thread, there is no well-defined logical time relative to which the response action can be scheduled. Therefore, we use a physical action, which will cause the event to acquire its tag not from the logical clock, but from the physical clock, which is just a measurement of physical time obtained from the platform. And this is what sets physical actions apart from logical ones. Now, you might think that this spells trouble. After all, we're introducing non-determinism, and we didn't want that. But let's have a look at our definition of determinism again. We have to keep in mind that the tags of the events scheduled on a physical action are derived from a measurement of physical time. And therefore, they're inputs to the system, just like the values associated with those events. The system reacts deterministically to these inputs, and the outcome of any further processing, assuming that reactions themselves are not a source of determinism, is exclusively determined by those inputs. So now let's have a look at what the rest of this program does. So we have an analysis reactor that is triggered by our sensor. Rather than doing actual work, it actually invokes microsleep. So it just waits. But it only does this every other triggering. The first time it gets triggered, it sets output Y immediately. The second time, it spends 500 milliseconds of physical time, and so on. And then finally, our actuator prints a standard out, but it also specifies a deadline. This is a predicate that gets evaluated once the actuator's reaction has been triggered and is ready to execute. It determines whether this reaction will execute or the accompanying deadline mishandler in the subsequent code block is executed. Recall at this point, the current logical time is still equal to the tag that was assigned in the sensor based on the physical clock. So no logical time has elapsed during the preceding reactions in the analysis component. They have all executed at the same tick. Now the predicate is as follows. If the current logical time plus the deadline of 500 milliseconds is greater than the current physical time, then the logical action is considered on time and it just executes. If the opposite is true, in other words, execution is lagging behind physical time by more than 500 milliseconds, then the alternative reaction is executed. So this constitutes a deadline miss. Now, with an analysis component that does actual work and an actuator that needs to respond within a bounded amount of time after seeing a sensor event, we need to estimate the worst case execution time and set the deadline accordingly in order to prevent deadline violations from occurring at runtime. So let's have a look at what our little test program here does. Again, compiling, running the program. So of course, the program alternates between reaching deadlines and missing them. So I'm providing input, but every other time I get a deadline miss because my analysis component takes too much time. And this again seems like an obvious source of non-determinism. But the point here is that the non-determinism stems from factors outside of the semantics of LF. Deadline reactions should be thought of as fault handlers. Hence, the assumptions on physical execution time, if those are met, then the system behaves deterministically. And for the case where they don't, we have a runtime error handling mechanism that is able to address the fault. So the reactor model that I was describing in my thesis offers a significant degree of freedom when it comes to scheduling. As highlighted in this little piece of pseudocode that describes part of the execution algorithm of the reactor runtime system, this select procedure has to draw a reaction to execute from a set of reactions that are ready, meaning that they're not blocked by other reactions that depend on them. Which reaction should it pick first? In the C runtime, we have implemented an earliest deadline first scheduler, and this simply means that this select function gives priority to the ready reaction that has the earliest deadline. And a multi-threaded implementation, as I describe it in my thesis, of a reactor runtime can map reactions without dependencies between them to different threads. making it straightforward to express deterministic parallel programs like these ones here. And our synchronous model works extremely well for regular workloads, but the barrier synchronization that happens at the end of each tick can become a problem if some of the reactions take a lot more physical time than others. And if we want to escape the synchronization barrier between synchronous reactive ticks, we could take advantage of the sparsity of our model. Remember, only triggered reactions execute at any given logical time. So if we scatter events across a timeline by assigning them a physical time rather than a logical time, then there will be a lot more asynchrony and non-determinism, but this would be non-determinism by choice. These physical connections are implemented as syntactic sugar. Under the hood, an AST transformation daisy chains two reactions paired with a physical connection. And the problem with this approach is that scheduling physical actions induces overhead, particularly because it requires acquiring a mutex lock for the event queue. And contention on this lock can be a real performance killer. We currently don't have a solution implemented for that yet, but I do have some concrete ideas of how to alleviate this problem. Another issue is that it would be very expensive to access the dependency graph at runtime to determine whether or not one triggered reaction depends on another. In order to avoid doing expensive graph searches at runtime, we developed a binary encoding that lets us identify overlap between chains in the graph simply by computing a bitwise AND with their IDs. The ideas in this diagram or in this graph are labeled I, and the L stands for level, which is essentially the maximum length of a directed path that it has to any node without dependencies. So as you can see, node F here can reach A, which has no dependencies, in 3 steps. But there's a longer path through E that takes 4 steps. Its level, therefore, is 4. Now, looking at the IDs, the node H consists of all ones, as you can see here. And that is because it's part of every chain in the graph. If we look at F, we notice that the level of F is greater than G, which would in principle suggest that an ordering between them. But because they're on different chains and the bitwise AND, as you can see here, is 0, we can safely execute them concurrently. And there are several pairs like that in this graph that have this property. So the programs that we've looked at so far are rather simple, and they're focused a lot on expressing timed behavior. How do reactors measure up against actors when it comes to more conventional actor programs? We figured out that the best way to evaluate this would be to implement some benchmarks from the Sabina suite, which is an often cited set of actor benchmarks developed at Rice. And we've only started this effort recently, so results are preliminary, but the results that we've gathered so far are promising. This simple ping-pong micro benchmark provides a measure of runtime overhead, essentially, and compared against Akka, which is a state-of-the-art actor framework written in Scala, which compiles down to Java bytecode and also exploits multi-threading. As shown in this graph, we dramatically outperform Akka. We're about 30 times as fast. And of course, this program doesn't allow for any parallel execution, so the single-threaded version of our runtime is obviously the fastest. The overhead in our multi-threaded runtime is very minimal. In this case, the extra thread are essentially ignored, and there's no contention. Another benchmark from the Savino suite approximates the area of a trapezoid, and it's a simple master worker setting where work gets distributed to workers. And there too, we're a good bit faster, sometimes between 2 and 3 times. It's not entirely clear to me why the C++ runtime, which is implemented by Christian Menard, by the way, is beating our C implementation, but that's worth a little investigation. I should say that the C++ benchmarks cited here were implemented by Hannes Klein as a part of his master's thesis that he just completed at TU Dresden. And in this graph, we can see that our runtime system achieves a near linear speedup on this benchmark up to the point where the number of threads matches the number of cores. There are other benchmarks from that suite that we have started working on where the results are less good, but we haven't yet been able to thoroughly analyze the results and much less attempt to implement optimizations to address any deficiencies. As stated before, one thing that is clear is that contention on the locks that protect the event queue and the reaction queue of the runtime system, that is definitely an issue. One of the things that Hewitt and Aga's actors are really good at is dynamically changing who they talk to. A reference from to one actor can simply be passed to another as part of a message, and given an actor reference, an actor can send messages to the actor that the reference points to. This situation is a little bit more complicated for reactors because reactors can communicate values through ports, but they don't control who is listening on the other side. In my thesis, I describe mutations, which are a special kind of reactions that have access to a set of privileged API functions for creating, deleting, connecting, and disconnecting contained reactors. The preservation of determinism is achieved through extra dependencies that are implied by mutations. These dependencies essentially prevent the contents of a reactor from reacting during or ahead of any mutation that might modify the content of that reactor. Support for mutations in Lingua Franca is still experimental and a topic of future work. We'll also need them to implement some of the Savina benchmarks. In Lingua Franca, it's also possible to specify a federated program. This allows for reactors to be mapped to different hosts. Just like with the after keyword that we discussed earlier, an AST transformation substitutes connections between federates with functionality that can handle the sending and receiving of messages through the network. The LF code generator generates binaries for each federate, plus a shell script that, when invoked, ships the binaries to the respective hosts through SSH and then starts a distributed execution. If we distribute our reactors among different compute platforms, then of course we no longer have 2 timelines to deal with. We have a multiplicity of them. And of course, with this many observers, physics gets into the way of knowing what the true order of events should be. But we can still preserve our discrete event semantics if we can ensure that each observer sees all events in timestamp order. And you might think, well, don't we have TCP/IP for that? But TCP/IP message ordering guarantees only apply on a point-to-point connection, which is insufficient to achieve our goal when the connection topology also has merge points like this one. If we choose centralized coordination, which currently is implemented, we have a central entity that is co-generated from the LF program through which all the messages flow and that controls the advancement of time. Of course, this central entity can form a performance bottleneck, and it can also become a single point of failure. Perhaps more interesting is our fully distributed coordination model, in which each federate controls its own advancement of time. And the question here remains how to ensure that all events observed are observed in tag order. the question boils down to the following. Given attack T, how much physical time should be allowed for reordering incoming messages from other federates such that after this time window, we can expect no more messages to arrive with a tag smaller than T. So you can see here in this diagram, X happens before Z, but it travels through another reactor, another federate, and the messages actually arrive at the receiver in the wrong order. But as long as we wait long enough and we reorder those events, then and not let the receiver start executing before that time, we still have this property of seeing all of the events in tag order. Now, this problem has been addressed in previous work. I think Carl already mentioned it earlier. This work is called PTIDES, and it's very similar to Google Spanner. It requires knowledge of the connection topology and which we provide in our model. And it also needs bounds on execution times, network latency, and clock synchronization error. And of course, since each message has a tag, it will be detectable when messages are received out of order. And we know that one or more of our assumptions with regards to these bounds have been broken. So in other words, we can have determinism, but under quantifiable assumptions. To reliably meet deadlines, we need to perform worst case execution time analysis and schedulability analysis. For deterministic federated execution, we likewise need bounds on physical time spent in the system. And in addition, we can use a logical time delays to lessen or even nullify the physical wait time until messages are safe to process. Delays can also be used to make the safe to process analysis a bit more modular. So future work, there's a lot of it. Of course, we can do a more thorough performance evaluation, and we've only started doing this, and we've only just recently started to develop the tools that we need for that, including a mechanism to do tracing and analyze execution traces. I bet there is still a lot of improvement that we can get out of our runtime. So as we implement more benchmarks, we should be able to improve the performance. The distributed execution is currently implemented, but implementing distributed systems is not easy, and there are lots of issues that pop up as you build these kinds of systems. So in the centralized control, for instance, we have the single point of failure, but in the distributed coordination mechanism, federates could disappear and we wouldn't even notice. So to make it more robust, there's a lot more additional work that is necessary to make distributed execution really practical. One of the things that we also realized was that, sure, in a very controlled setting where where you can rely on PTP or another time synchronization mechanism, then a lot of this can work with very tight error bounds. But most users might not have that kind of infrastructure, and it might be a good idea to implement some of these things inside of the runtime system. So if we could have time synchronization as part of our federated runtime system, that could be a real advantage and lower the barrier to entry. Another issue in federated execution is security. So we have some rudimentary ways of preventing federates from joining the wrong federation, but not very much attention has been paid so far to security. There's some recent work by Hook and Kim about managing security through the use of edge computing. And it seems that many of the concepts in that work could also readily apply to Lingua Franca and have the potential of being integrated with the runtime system as well. As I mentioned, in my thesis, I described mutations. We haven't fully implemented them yet. Whatever we have done so far is pretty experimental, and there's still work that needs to be done there. Another thing that would be pretty high on the list would be to target precision time hardware. So that we have already run some tests on PATMOS. We have also, and this is actually work that one of our students, Shaokai Lin, has started to dust off the FlexPret implementation that was written by Michael Zimmer. FlexPret is another precision time machine. And because we feature time as a first-class citizen in our language, it would be a really good match with a processor like that can guarantee precise error bounds and timing. There's actually a deadline instruction set, a deadline instruction in the instruction set of FlexPret that could map nicely to our deadline mechanism in the language. Another thing is that the EDF scheduler that I mentioned it's not preemptive. So everything, every reaction runs till completion. We can't say, okay, we have something more important to do now. This reaction stops, and then another reaction takes over. But there are ways of achieving something like that by using a preemptive thread scheduler underneath. So if we have more threads than cores, we should be able to tweak the priorities of threads at runtime, and then give priority to threads with earlier deadlines. And this is something that will probably not be very portable, but it would be interesting to see what kind of results we can get out of that. Another thing is that a lot of this analysis that needs to be done to reliably meet deadlines, to make sure that federated execution works well, relies on analysis that we currently don't have in the compiler. So it would be really interesting to see if we could integrate any kind of worst case execution time analysis as part of our framework, so that we can give early feedback to the programmer about that. So to conclude, reactors and lingua franca can augment mainstream programming languages with deterministic concurrency based on synchronous reactive principles, give it a rich model of time, a scheduler that can handle periodic tasks as well as sporadic events, deadlines, high-performant automatic parallelism, deterministic runtime mutations, and also federated execution. And before opening up for questions, I'd like to say that if you're interested in learning more about lingua franca or to follow the project, you can visit our GitHub using this URL. Thank you. And any questions?
So yeah, I'd like to maybe moderate this a bit. So please use the raise hand feature in Zoom to ask questions. I guess I'd like to just start with a comment more than a question, which is the bullet list that you gave on your further work slide is in some ways to me the most exciting part, right? I've always felt that some of the best research is the research that leads to many good questions, that doesn't just sew up a field, but rather opens up enormous opportunities for many other people. And I think that this was in some ways part of the challenge here is that these are all very exciting questions, right? These are major research topics that could lead to another PhD thesis. And it's very tempting to just keep working on them, which is partly why I had to arm twist you to actually
exactly what happened.
write your thesis now rather than solving all these problems first and then writing a thesis, because this could take you another 10 years.
Yeah.
But to me, this is really one of the most wonderful things about this work, is that these opportunities are kind of amazing for a lot of very interesting follow-on work. And that doesn't in any way diminish what's been done so far, which I think is really quite impressive. But it's really, I mean, it opens up a lot of opportunities. So yes, so we have several questions. So Chris, I see Chris Gill has his hand up.
Great, thank you. So Marten, you had mentioned that order of declaration is used to distinguish between otherwise simultaneous reactions. And I'm wondering if your declarations all have to be in the same file in Lingua Franca.
So the scope at which these declaration orders matter is a reactor. And
within a reactor.
Within a reactor. And you can certainly have reactors defined in different files. And we've also started to build, we have an import system. And so you can, the scope is the reactor, in short.
So even there, though, I mean, sort of there's this interesting tension between, good software engineering practice, which says, don't make your, entities sufficiently complex that you would need more than one file to to declare them. And yet, in the real world of software practice and experience, sometimes they get really huge for sometimes actually good reasons. Do you allow multiple, files to sort of break apart a reactor into sort of subsets of declaration, or?
So to an extent, we do feature inheritance. So it is possible to define a reactor in one file and then extend it in another. But the declaration itself has to be fully in one file. I'll tell you something about this notion of ordering reactions. It is, first of all, I mean, it gives us freedom, but it also gives us some pain. Because when you write a reactor and you put it in a system, you connect the wires, you might actually find that you introduce cyclic dependencies between reactions, not even because necessarily the way you arrange the wires, but also because there are these order dependencies between reactions. And you sometimes need to swap their order in order to for the program to be allowable. In most cases, it makes perfect sense, but it's not the first thing that occurs to you. So what we found was that this diagram synthesis tool is actually invaluable in providing the feedback, because when this happens, we actually literally show a cycle in the graph, and we have also the ability to filter out the parts that don't matter. And then it's crystal clear what the problem is. But these are problems that, as a reactor programmer, you run into that are unfamiliar if you're, just doing objects or actors or, things like that.
That's very cool, actually.
So yeah, I wanted to give a little shout out to Alexander Schultz Rosengarten, who's also here, because he's the key guy behind that diagram synthesis, and it has really been an incredibly valuable addition. It really helps in developing intuition about these programs. I think Sanjit Seshia was next. Sanjit?
Yes, hi, can you hear me?
Yes.
Okay, so Marten, excellent talk and very nice work. And I want to second what Edward said about the future work. You have really an exciting set of directions there. So my question is about determinism and lingua franca, and I apologize if part of your talk answered this because Zoom has been flaky on me today. So I've been having a drop connection now and then during your talk. Okay, so the question is, your definition of determinism relies on what exactly you define as state. right? I mean, you're saying that the next state is a deterministic function of the current state and the input. But often in systems, even non-deterministic systems we think of as being very non-deterministic, one can argue that they are deterministic at some level if you include sufficient state in it, right? If you expand your notion of state. And so I'm just wondering, in the context of lingua franca, if the language provides any support for the programmer to understand exactly what state the program is going to be deterministic with respect to, so that when you run it, you have a clear expectation of the behavior. And at the same time, when you run, for example, any verification analysis, it's also easy to check the property of determinism.
Very interesting question. Thank you. So one thing that we certainly do in reactors is isolate state. So just as with actors, actors can only manipulate their own state. And they can't just manipulate the state of other actors. They can only send a message. We have this same principle in reactors with the catch that reactions within a reactor do have shared access to that state. And the way a state evolves has to be considered from the start of a synchronous reactive tick to the end. And so anything that happens in between is not part of the state transition. It shouldn't be part of if you were to create a transition system, it shouldn't be part of that.
Can you say that again? I didn't quite catch it. So again, what is the, if I were to write an LF program, right? Then what would be the state with respect to which its execution is deterministic? And one of the things that I worry about is if you can embed arbitrary C code inside the reactor, then it becomes even harder to understand what is the,
yes.
the state. Yeah.
So when you define a reactor, I can actually go to I had it somewhere. Yeah. So reactor is this tuple: inputs, outputs, actions, state, reactions, mutations, contained reactors, a priority function, and the startup and shutdown trigger. So with state, we mean explicitly declared state.
Okay.
That is what we can protect. But of course, I mean, by the time that you embed arbitrary C code inside of a reaction, right. And if that code is not well behaved or does something under a table using a shared variable, then all bets are off. But this is a trade-off. We're not trying to, in this case, to be bulletproof. We try to provide abstractions that programmers can follow and prevent mistakes. Any kind of intentional subverting of the model of computation is not really, can't really be enforced in a language like C. We probably have a much better chance of doing that with a different target language, such as Rust, for instance. That would provide us, much stronger guardrails.
Right.
I think Sanjit's question is he's using state more broadly than you're using it here in the context of a reactor definition. And I think maybe the definition of determinism said that there is exactly one behavior, not that there was exactly one sequence of state transitions. You have to define what you mean by behavior in order to talk about whether a model is deterministic or not. And if you choose to define behavior in terms of state transitions, you need to clarify which state transitions you're talking about. Are you talking about the transitions that occur in the registers of the machine executing the C code? Or are you talking about the assignment of values to state variables in reactors? Those are very different levels at which you might talk about state transitions.
Mm-hmm. Yeah, I would love to have a longer discussion. I don't want to take up all the time here we have for Q&A, but I would love to have a longer discussion with both of you about this. And I look forward to the discussion about this in your dissertation as well, Marten.
Okay, perfect.
So thank you. And Marten, thanks for bringing together this audience as well. It's great to see so many friends here. So hello to all of you.
So I think Carl Hewitt had his hand up next. Carl.
Oh, well, thank you, Marten. That was a very good talk and excellent work and well worthy of a dissertation.
Thank you.
But I don't think that your criticism of actors is quite correct. And I put a link in the post of how to correctly implement an important example that I got from you guys. Been following your work for a long time. Work that Ed and his whole group has been doing that for many years. Of the train with the doors, right? You don't want to start moving the train when the doors might be open. You don't want to open the doors when the train might be moving. That's an important example. So I explained there's an article, I put a link to it, how to correctly do that in actors. And more generally, I think that there's a larger debate to be had here between these two different approaches, the asynchronous and the determinate approaches. There are complicated trade-offs going on back and forth, as we mentioned at the beginning. And I think that the two approaches can learn a lot from each other as we go forward. But I don't think that you shot the asynchronous approach dead in the head, right?
No, that was also not my intention at all.
Yeah. You can prove things about that using actor induction just as easily as you can prove things about these things. So I don't think provability is an issue. There are other more complicated issues. I think that modularity, robustness, and performance are going to be the key issues going forward. And I think there's an important debate and even a collaboration to be had between these different approaches. One thing I do think is valid, and Go might agree with this, is that the actor approach many of the actor work has neglected time, okay? It hasn't paid sufficient attention to time, particularly the time at which it gets inputs from the outside world. And that's a critical piece of provenance that needs to be taken into account. Now, I wouldn't put it in as a central part of the system everywhere, but I think it has been neglected in actor systems, and that's an important thing. And maybe Gul has a comment on that, I don't know.
Yeah, so I guess the notion of time gets complicated. I think one way to think about this is what you're doing is raising the granularity of the determinism. So in the standard actor model, an individual actor is deterministic with respect to a single message. And the arrival order of messages is what's determining is causing the non-determinism. Now what you're doing is to sort of specify dependencies and scheduling between some groups of actors. And the non-determinism is now pushed out to the inputs from the outside world that you obviously don't control. And what you're doing is sort of starting your definition of determinism, so to speak, from the time that the message arrives. So, so I would sort of look at it as sort of raising the granularity of determinism to make basically use the predictions. Do you think that captures it reasonably, or?
I think that that's a very good way of explaining what we're doing, actually. I think that the key thing that this approach enables is that you can define the boundaries of your system, implement it, and then also test it at the boundaries, right? So what this allows you to do is to build a suite of regression tests, have a component that is not just one actor, but a more complex system that responds deterministically to potentially sporadic inputs, and still you'll be able to test it using the ordinary testing means that we currently have in software engineering.
Right. I had some other questions, but well, let me ask the one just related to this, which is what do you do about errors and fault recovery? So you have some logical rules regardless of the timing, where if X doesn't happen, Y shouldn't happen because that would cause a catastrophe. Now there is a timing, but if the timing fails, you sort of have forward error recovery, and then you have a sort of a new time horizon. So do you have to sort of then redefine it in the semantics, or is it all explicit? Is there any implicit abstractions?
So the deadline mishandler gives you a handle to respond to these kinds of problems, right? And it's an interesting question, because it would be very tempting to say, well, however that recovery is implemented should be application specific. So kind of like, it's not our problem. But as soon as you observe these kinds of problems in a federated execution, there might be, you know, it's not that clear cut anymore. So I would say that is still an open research question.
Right. I mean, sort of the standard exception handling is not quite good enough, because you now have these additional timing things and cascading drops. You obviously don't want the train to move if the doors haven't closed, for example, even though there's a timing deadline for the train to move.
Right.
So there's some kind of cascading effect. And the question is, well, your exception handlers now, do they need to restart their clocks? Do you do sort of incremental scheduling, update your schedules dynamically or statically, or?
Well, I mean, we can't stop physical time, right? And the execution is driven forward by physical time.
Right.
So we can't do any of those things, but I guess
But you do have to stop the train.
Sure. Well, that's
right.
exactly the point I was going to make.
Right.
We have this issue of we're not implementing a distributed database where if a transaction arrives too late, we can just undo it. Because if the train is moving, it's already too late.
Right.
Therefore, we have to have this, kind of this, hard preemption of certain particular, actuations. And that's what this deadline mishandler is for, is to say, well, okay, you're not on time, so now I'll give you an opportunity to do something else, because whatever you were planning to do probably isn't the right thing to do right now.
Yeah, it raises interesting issues for adaptation, especially if you have an AI system or something. How do you then recheck what's the new schedule and if it's feasible?
Absolutely. I think that we'll learn a lot about that by the time that we get to implement some demonstrator applications and build some more complex systems. Right now, the effort has been building the model, building the language, implementing the compiler. There's been a lot of implementation work that had to be done before we even got to this point, and we're now starting to see where we can actually be a little bit more focused on applications, and that starts out with benchmarks first. But after benchmarks, we might want to build something real.
Right. So just on the notion of time, I had some more questions. I don't know, Ed, if you want to keep some order, or I should just continue.
So Edward's moderating.
Yeah, why don't we have one more question, and then we can release Marten and take the rest of it offline.
Okay, sure, yeah.
Yeah.
So just in terms of this, you have a nice model of sort of multi-scale time, sort of the larger steps and smaller steps. This also kind of suggests the possibility of a hierarchy, because obviously some things need to be more tightly synchronized than others, so that the question of scalability comes in. For example, if you have a central coordinator, then it's not just a single point of failure, it's also time has to be stretched forward. So actions that the central reserve takes in a certain time frame, action that interest rates, how they're changing minute by minute, is a different time scale. So there's sort of this hierarchy of timescales in any system, and you get systems of systems, and so there is sort of this possibility of sort of extending the semantics beyond sort of these two levels, where you have a multi-scale model, and they are of course interacting with each other.
Yes, I agree. I think that there are some really interesting research opportunities there. I guess what I would say for now is that one of the things that we rely on is that the progress of physical time, the Newtonian physical time that runs in the background, is something that we can always rely on, regardless of clock synchronization error and issues like those. So one of the things, for instance, that we explicitly disallow is the scheduling of a logical action in an asynchronous thread. In a federated execution, that would be deeply problematic because you would have one federate that would lag behind, arbitrarily behind physical time, and that would let the other ones come to a grinding halt as well. So this notion of having this kind of being tethered to physical time seems to address a lot of problems, but more research is definitely needed.
Right, and I think you have the start of it with a two-level hierarchy, and that could be extended to allow scalability and more federated, where you have synchronization, but you could be off by a larger unit of time.
Mm-hmm.
In terms of the ordering.
This is particularly a place where this work diverges from this rather long, well-established field of distributed discrete event simulation, which actually provides the foundation for the centralized coordinator. So the centralized coordinator in Lingua Franca is fashioned after HLA, which I learned all about from Jeanette Cardoso, who's here on this call as well. Originally, she's the one who taught me all that. But as you said, Marten, the key difference here is that the advancement of physical time forces things to be progressing regardless of the behavior of the individual components. And that, I think, is a very interesting and rather unique feature of this mechanism.
Very nice. Yeah, go ahead. Yeah.
So with that, I think we should declare success and do a virtual applause for Marten. Nice job. And
thank you all for attending.
Yeah.
Thanks very much, Marten. It was great. Thanks, Marten.
Thanks, Gil.